This is the review for chapter 16, acid-base equilibria. So before starting the chapter, I'm just going to look at a few properties of acids and bases. Obviously, the properties of acids and bases depends on the type of acid or base being discussed. Generally, acids are sour, and both strong acids and strong bases can be used to corrode, not corrode things, but to dissolve certain types of metals and materials. And we're going to look at the ways that acids and bases can form equilibrium. So in the chapter before, we talked about writing out equilibrium equations where we have the double arrows. So it's going to be the same thing. And remember the rules for writing equilibriums. It's going to be products. This is just going to be important. It's going to be products, concentration of products, with the concentration of the reactants. That's the key to all equilibrium expression. So moving on to the next page. I'm going to erase this here. Chapter 1, Arrhenius acids and bases. So just like I said here, acids have the sour taste, bases are bitter, and they can feel slippery. Soap is an example of the base. The person that invented the Arrhenius theory, obviously his last name was Arrhenius, Savante Arrhenius. You don't need to know that name, not important. But what he said, and this is important, is that acids are substances that produce hydrogen ions in water, and bases are substances that produce hydroxide ions in water. So this is the hydrogen ion, and then this is the hydroxide ion. So this is just restating that an acid is substance. This is the whole key to the theory, is that an acid is giving away a hydrogen, and in turn the base is accepting the hydrogen, and then the base is increasing the concentration of the hydroxide ions. Hydrogen chloride, so that would be HCl, is a good example of this. So when it's dissolved in water, the hydrogen breaks up, and the hydrogen chloride breaks up into the hydrogen ion and the chloride ion. And obviously, since it's dissociating into this hydrogen ion, the concentration is being increased. So it's a good example of an Arrhenius acid. This hydrogen we'll see on later that the hydrogen can be replaced by this, which is H3O plus, which is also called hydronium. Oh, didn't fit it in there. And we'll see that later, and that's because the hydrogen here gets bonded to that and it forms the hydronium ion. But generally, sometimes that's not written like that because the water does not get included into the reaction. But just so you know, in case you see that, they can be used interchangeably. The aqueous solution, blah, blah, blah. Okay, good Arrhenius base is sodium hydroxide. Sodium hydroxide, the formula for it disassociating is going to be NaOH yields Na plus OH minus. And then again, since it is creating that hydroxide ion, it is increasing the concentration, so it is an Arrhenius base. And notice the big thing here is that since this is a strong acid, hydrogen chloride, and this is a strong base, sodium hydroxide, neither of them are at equilibrium because the arrow is only one direction. And that's because they dissociate so much that they're not going to form an equilibrium because there is no backwards reaction. It's only a forward reaction for strong acids and bases. So going on to the next page. Section 2, Bronsted-Lowry acid and base definition. So this is another definition, just like the Arrhenius definition, created by Thomas Lowry. Again, don't need to know the name. And this is based on the transfer of a H+ ion from one substance to another. So I said before, or I alluded to it at least, where that hydrogen is going to be transferred to another substance. Technically, the Arrhenius theory is just saying that the hydrogen concentration is going to increase, and this is taking it one step further, but they're both correct. But you can derive Lowry's way of thinking from the Arrhenius way of thinking. So you're going to have an acid and a base conjugates that are going to transfer this H+ ion from one to another. So let's look at some examples of that, hopefully. Okay, the H plus ion in water. So we're going to look back at hydrogen chloride. We said before that it dissociates into the hydrogen ion and the chlorine ion when we were talking about the Arrhenius theory. The hydrogen ion interacts strongly with any source of electron density. So like I said, this is how you're going to get your hydronium ion. Remember, this is H3O plus. And that plus just comes from the extra hydrogen that's there, and it doesn't bring along an electron. So it's got one more proton. Remember, protons are positive, electrons are negative. So you're adding a proton onto the hydrogen, but you're not adding an electron. So you've got that plus charge here. That's where that comes from, just in case you were wondering. Okay. So now we got the hydrogen ion plus the water, and there's no electrons around it. So what it's actually going to do is it's going to steal one of the electrons from the hydrogen, and they're going to form a bond. It's going to form an OH bond with those two electrons. Because remember, each side of this bond represents an electron between the two. So that's how the hydronium ion is formed. How this ties in with the Bronsted-Lowry theory is that it involves the transfer of a hydrogen ion. The hydrogen is starting out as a hydrogen ion, and it's being transferred to the water molecule to form the hydronium ion. Okay. For example, bonds in addition. Okay. This is just talking about further ways that hydrogen ions can bond with other substances. That's not generally important. It's just an example of that. Chemists use the notation that, okay, yeah, this is what I was talking about, where hydrogen and hydronium can be used interchangeably. And it's gonna be the same thing because the ratio between the hydrogen ions and the hydronium ions will be equal, because let's say you have 5 moles of hydrogen ions, you can only create 5 moles of hydronium ions, because each of those hydrogens can form one hydronium ion. Okay, moving on. Talking about the proton transfer again. Anytime you see proton transfer, automatically think H plus. The reason that's considered proton transfer is because, remember, hydrogen has one electron generally and one proton, and then the H plus is the hydrogen without that electron, so it's only got that proton. In the reaction, blah, blah, blah. Okay, so this is hydrogen chloride. It's going to dissociate, remember? Hydrogen chloride yields H plus Cl minus. That's from the Arrhenius theory. Okay, now we're going to take that one step further, and we're going to add the water that it's submerged in into the reaction. Remember, sometimes this isn't included in, but for this case it is. So that hydrogen that it's going to disassociate into, instead of it just dissociating, it's going to bond with this H2O molecule and form the hydronium molecule. And that is the key to the Bronsted-Lowry theory. And you'll notice is that this hydrogen is gaining, or this hydronium gained an ion, this hydronium gained a proton, and this chlorine lost a proton. And then, oh, what did I do here? Sorry about that. This hydrogen chloride is going to give up a proton, and this water is going to gain a proton. So here's the transfer. It's going from here to here. The hydrogen is going from there to there. And then it's going to leave you with the Cl and then the H3O. That's the biggest thing. Just know that there's that hydrogen that's transferring, and that you have to include the water, and that's how you get the hydronium ions instead of just the normal hydrogen ion that you'll get with the Arrhenius theory. So let me erase this. This bottom structure is just showing basically what I just said, where you got the hydrogen, it's going to attach the water, form the hydronium ion. Okay. So moving on. notice for the reaction proton donor. So HCl is a proton donor again, because, why do I keep clicking that? Because it's giving up the H plus ion, which is the proton, to the water to form the hydronium ion. An acid in the Bronsted-Lowry theory is any molecule that donates a proton to another substance. Biggest way to think about it is to just think of an example. So hydrogen chloride, you know, is a strong acid. Why does it fit the Bronsted-Lowry theory, Bronsted-Lowry definition of an acid? Because it has that hydrogen that it's going to give up. The base is a substance that accepts a proton. So think of sodium hydroxide and NaOH. So the NaOH is going to accept the proton and form the water. You know what? I'll give another example. Water in this definition, or water in this example, would be a Bronsted-Lowry base because it's accepting the proton. I know it's weird to think of water as a base, but in this definition, because the definition is a substance that accepts a proton, the water is what's accepting the proton from, I keep clicking that, from the hydrogen chloride, and that's why it's a base in the Bronsted-Lowry sense. Here it talks about that actually, where the water molecule serves as the proton acceptor, and that's why it's a Bronsted-Lowry base. It's another reaction talking about, again, hydrogen chloride is the acid because it's donating this hydrogen. Ammonia, which is NH3, is the base because it's going to accept this hydrogen from the hydrogen chloride to form ammonium, which is NH4 plus. Some examples. Again, this is showing exactly what I said. Ammonia is the base in this case because because the water is going to donate a proton or an H plus ion, hydrogen ion, to the ammonia, and it's going to form ammonium, which is NH4 plus, and then the water is going to form the hydroxide. So even though the water is increasing the concentration of OH, it's technically an acid when you're talking about Bronsted-Lowry because it donated the hydrogen. Okay, and that's the important difference, is that it's not just increasing the hydrogen or hydroxide concentrations in a substance. For the Bronsted-Lowry theory, it takes it one step further. Okay, moving on. Conjugate acid-base pairs. So just talking before, you have a substance that's going to, think of this as like HCl. Oh, bad writing there. HCl. The A would be the Cl, obviously, and then the H would be the H. So the HA is going to give up the hydrogen to the water. HA would be the acid. H2O is going to be the base. It's going to give up the H to the water and form the hydronium ion. And then it's going to be left with an A. So again, this is your acid. This is your base. Oh. It's really difficult to write on this. Okay, now we're going to look at the conjugate pairs that form by it. Biggest thing to remember is that here we'll look at it down here. A acid originally is going to form a conjugate base. So whatever it starts as, the conjugate is going to be the opposite of it. And that is because if in an equilibrium reaction, think of it like this. If you have the acid and you're getting rid of the hydrogen, okay? So the hydrogen is going to the water, H plus, it's going to the water, and you're left with something that no longer has a hydrogen. So think in the reverse reaction. Now, if the reverse reaction is going to occur, what's going to happen? One of the H's from the hydronium ion is going to go from the hydronium ion to the nitrous ion. I think that's nitrous, NO2, to the nitrous ion. So in that case, the hydronium becomes the acid, and the nitrous becomes the conjugate base to form nitrous acid. If that's too hard to follow, just remember acid forms conjugate base, base forms conjugate acid. It's the opposites, okay? Okay, there's just some more examples. Okay, next page. Relative strengths of acids and bases. Some acids are better proton donors than others. So it's important to know your strong bases. Hydrogen chloride is the best example of a strong acid. And then they'll always try to trick you up with hydrogen fluoride. Hydrogen fluoride is not a strong acid. So I'm going to write this right here. HF is not a strong acid. Okay, in other words, the stronger an acid, the weaker its conjugate base. Okay, so this is something, it's easy to just know. The stronger that an acid is, the weaker its conjugate base. The stronger a base is, the weaker its conjugate acid. So the stronger that a substance is, the weaker its conjugate. Strong substance, weak conjugate. So you're gonna have something like HCl, which, like I just said, HCl, which is a strong acid, has weak conjugate base. Remember, acids have base conjugates. Acids, base conjugates, it's opposites. And since this is a strong acid, it's going to have a weak conjugate base. Likewise, HF, which, like I said, is not a strong acid, is going to have a relatively stronger conjugate base because it's so weak of an acid. The inverse relationship, blah, blah, blah. Strong acids defined as something that completely dissociates. So remember I said that strong acids don't form equilibriums, and that's because it's not going to have the ability to go back and form the original substance. So HCl, best example of a strong acid, is going to 99.99999% of the HCl molecules are going to dissociate into H plus and Cl minus. HF, on the other hand, will be able to form some sort of equilibrium because parts of the HF concentration will not be dissociated into hydrogen and fluoride. They will just stay as H and F. Again, this is like I just said, it only partially dissociates. That's the biggest thing to know. Weak acids only partially dissociate. Conjugate base of a weak acid is a weak base. It's a weak base, but it's a stronger conjugate base than that of a strong acid. Substance of negligible acidity contains hydrogen but does not demonstrate its conjugate base is a strong base. Okay, so again, something that's very, very weak acidity has a very, very strong conjugate base. So if it's an acid, it has a base conjugate. If it's a strong acid, it has a weak base conjugate. If it's a weak acid, it has a strong base conjugate. So it's just opposites for that. It's the biggest thing that you need to remember. Opposites, opposites, opposites. The ions, hydronium. Okay. Trying to look at the biggest things to touch here. Touch on. So this is just talking about determining which is going to be the acid and which is going to be the base. Obviously, from this, you can tell that the HA is going to be the acid. HF, H2O. Okay, this is just talking about the relative strength of the conjugates. So if HA is a strong acid, A minus is going to be a weak conjugate base. Hydronium is going to be relatively strong of an acid because this is going to be relatively weak of a base. And that's basically what we discussed up there. Okay. And it's weird to think that hydrogen would be a stronger base than chlorine. But again, hydrogen chloride is just so strong of an acid that it's going to be so weak of a base. So next thing, just remember opposites for that. Opposites, opposite, opposites. The auto-ionization of water. So we talked about water a little bit here, but the biggest thing to know for water is that it can act as a acid or a base, and it's going to show it here. So a water molecule can donate a proton to another water molecule. So in one case, in this case, it would act as an acid, one of them, and it would also act as a base. And they're both weak, so you're going to see some sort of equilibrium here. And going off the Bronsted-Lowry theory, definitions, we're going to have this acid water molecule. It's going to donate a hydrogen to this acid water molecule. So this is just going to form the OH minus, and this is going to gain the H, and it's going to form the hydronium H3O plus ion. This process is called autoionization. Basically, autoionization is when water acts as both the acid and the base, and they combine together to form hydroxide and hydronium. Not really a lot there about that. Oh, went too far.